So coming from our last topic, we sort of ended there talking about how we can go from these probability distributions for discrete variables to continuous variables. And that sort of brings us right into the normal distribution. So this is a sort of generic looking distribution that's based on having a mean of 100 and a distribution of 20. So as long as I have, if I know the mean of 100 and a distribution of 20, I can actually use that information to then go through and compute the density function, that function I showed you at the end of the last lecture, topic. I can compute then the density. Density is really just, what is the area under the curve for that value, right? So I can compute that for the ranges of all scores that are in this variable that has a mean of 100 estimation of 20. So notice that the mean is right at the center because it actually is the most probable. Sort of like the 7 when rolling 2 dice. The 7 is the thing that was most probable in a distribution for rolling 2 dice. The mean in any distribution like this is going to be the thing that's the most probable, or that has the largest area under the curve. I like this. Someone sent this to me as a meme, I think on Facebook or Instagram or something. There's a normal distribution, and then here you have a paranormal distribution. It's silly, but in a topic like stats, you have to find humor wherever you can because it's not always sort of fun and games. But okay, so this is what we're sort of talking about, this sort of normal distribution, and we have sort of areas under the curve and all this stuff, but what can we really do with that stuff? So I had mentioned, again, this before, where, if we're trying to plot this out, if we're trying to find the normal distribution for a variable x, I'm going to plot out on the horizontal axis all possible x values that are known, at least the ranges that are known. And on the vertical axis is this thing called a density function, which really just talks about the area under the curve, which in and of itself is not super useful. To figure out the density for a single value is not super practical or useful for anything, but it can be converted into probability or proportion. So defined from the last topic here, again, the function of x, this density function, again, you don't need to memorize. The main takeaway here is that it relies on the standard deviation and the mean of the distribution, and then we can actually figure out the density from it as long as we assume it's a normal distribution. So just to illustrate a little bit more, I guess I don't have it, I did. There is, again, the value for pi is a given to known number. You don't have to, it's not something you have to calculate, it's just a given value, and so is e, where e is the anti-natural log. It's a value that is a known given number as well, and we can use that then to figure out the density. All right. So the characteristics of a normal curve, you actually can't see what it says up there, it's very, very faint. So just up here it says the mean, median, mode are all in the center, and the data is symmetric. So we're looking at, if it's symmetric and the mean, median, and mode, remember the median is the number that's at the 50th percentile. So if the mean and median and mode are all the same, it means that where you see the peak there, that's the mode and the median and the mean all together. That tells us that in a normal distribution, because the median is there in the center, we should expect 50-50 in terms of half the distribution is above the median, half is below the median, and because the median and the mean are the same, that's also true for the mean. Okay, so we know that normal distributions are bell-shaped, they're symmetric, they're unimodal, and the mean, median, and mode are all the same. And the trick to this is more of a sort of theoretical distribution. This is why I say that if we assume that it's normally distributed, we can then we can use this density function to our advantage. But no real distribution, right? So if you actually look at scores, none of them are going to be perfectly normally distributed, but many are sort of approximately normal, and they're sort of close enough to normal for us to be able to apply some of what we're talking about today. And you may see or read or in places as you go forward in psychology that this idea of assuming that data are normally distributed can be a bit contentious. There are lots of people that don't believe in using normal distribution theory to apply to data, and they have different ways of sort of doing things. That's fine. Just that normal distribution theory statistics is used so often. It's very sort of prolific in a lot of the sciences that you still need to understand how it's used and why we use it. Even if you choose not to, you still need to understand where it's coming from so that you can actually have an informed opinion about the conclusions drawn from tests based on normal distribution theory. Basically what I'm saying here is it's everywhere. You're going to see this all over the place. Anytime you see somebody using a t-test or an ANOVA or regression and any number of even correlations, all these things are all assuming that data are normally distributed. Another way of thinking about that too, if you don't like, assuming that we're always sort of forcing things into this normal distribution theory, the idea that data are going to be normal really comes down to assuming that you also have a large number of people, right? So again, when I say that no real distribution is perfectly normal, because oftentimes when we're talking about samples are small. There's not enough of them to really sort of come out to be a normal distribution, but they're going to be pretty close a lot of the time, which is why we tend to still assume normal distribution even when it looks like they're not perfectly normal. And even then, most of the tests we're using are not assuming that the distribution itself is normal, but that the statistics that we compute about those samples will distribute normally. And we're going to talk about a lot more about that in the next section on sampling distributions. So even though we're saying we're assuming a normal distribution, it doesn't necessarily mean that we're assuming normality on every individual sample or something that we're using, but normality will come into play at some point. And it does permeate everything. It's sort of everywhere, all over the place in research. So here is a way of thinking about generic normal distributions. Every normal distribution is going to have the same basic sort of format, where in the middle, near the hump, and there's these very faint lines you can see that in the middle, right at the peak, is going to be the mean. I'm just drawing this out in terms of population values, but this is mu here. It's the mean of the distribution is going to be right at the center. Again, the mean, median, mode are all going to be there. Moving away from there, going up to the right, it's going to be at equal intervals. You're going to have the mean plus 1 standard deviation, the mean plus 2 standard deviations, plus 3, plus 4, and as you go further away, the more standard deviations away from the mean you are, the lower the density, the probability gets lower. The curve starts to come in, and these things become less and less likely, less and less probable. Which is why when people talk about things like even like IQ, where you say, well, I'm 2 standard deviations above the mean in IQ. So the mean of IQ typically is 100. Standard deviation is usually around 15. So if you're right here at the mean, your IQ is roughly 100. If you're 1 standard deviation above the mean, it means you're about 115. And you can see that you're less likely to be at 115 than you are to be at 100. And then you also, if you're 2 standard deviations above the mean, you're now in a part of the distribution that's very, very small. The area on the curve is small, so your likelihood of being there is very small, which also means that the amount of people that are also there, there's not a whole lot of people that are going to be at that point. You get to 3 standard deviations, and now you're talking about almost no one. Your IQ is so high that the probability of you having an IQ is so low, there's not going to be a whole lot of other people that are going to be at that range of IQ. So we tend to talk about things a lot like that in terms of even when you take tests like achievement tests or things like MCATs, LSATs, those kind of things, we tend to think about where are you relative to the sort of average responder, and we tend to, people that end up going to law school or med school or that kind of stuff are people that are quite a distance away from the average responder and show that they're in a low probability sort of range up at the top. Okay. So when we say that lots of things sort of follow this idea of normal distribution, that someone I don't know who, this seems sort of a crazy thing to do. If you were to sum the last 4 digits of the numbers in your cell phone's contact list, so take everyone that you know, the other contacts, and sum up the numbers. What you're going to get is a distribution that is, again, look at this. This is not normal in the sense of being perfectly normal, but it does have the general sort of normal distribution shape. There's going to be very little numbers that are going to be huge like this, very little numbers that are going to be tiny, like near 0, and a lot of numbers sort of in between that are in these ranges of, I don't know, 16 to 21 or something like that is where a lot of the folks are going to be in terms of summing their numbers. So if you were to do that, even those kinds of things will follow a roughly normal distribution. Even though this is not perfectly normal, it's normal enough. It's close enough to a normal distribution that we can apply certain things and be able to figure out probabilities for the different ranges of digits here based on what we know about the normal distribution. All right. So again, going back to this idea of a normal distribution, I'm just using the example where we have a mean of 100 and a standard deviation of 20. Actually, one thing I do want to mention before I move on is that another thing that is common, and I don't know if it's easy to see on here or not. If I can see it, but they're very faint. There are lines that are going down here, and they're very faint. Somewhere right about here. Okay, and then the same spot on the other side, if I can see it, somewhere right about here, okay, is where, if you notice that the curve is sort of going down, and at some point it starts to curve back to curve out like this. There's a point where that occurs, and these things are called inflection points. Right, we have them on both sides. The inflection point is, again, where the curve starts to go from being, like usually when I draw, it starts to go from going down to then going out on distribution, down and out. At some point in here somewhere is the inflection point. So when my face is red anyway, when we draw out normal distributions with standard deviations, again, we tend to put the mean, mean's right in the middle. If I'm just drawing a basic one out, where I put one standard deviation is going to be right wherever this inflection point is, or some close to it, is where I'm going to put one standard deviation sort of above and below the mean is going to be here. So here's my +1, here's my -1. And then I'm going to go about an equal distance to -2, and again to 2. You get the idea, sort of how it moves away from the mean. So those inflection points, if you're ever trying to draw a normal distribution, right? Imagine where that line goes like this, and where your hand starts to have to sort of move. That's the inflection point. That's where +1 standard deviation goes. Here's the inflection point here. That's where -1 goes. So those inflection points are roughly somewhere around where the standard deviation marks are away from the mean, with the mean directly in the center of the distribution. Okay. Okay, so now we're back to talking about this distribution that has a mean of 100, standard deviation of 20. So you can kind of see with these very faint lines here that, right around where the inflection point is here is where one standard deviation above the mean is, with the standard deviation being 20. You get about the same distance above that. You got another 20 to the next standard deviation above that, and so on. I have this drawn out to 4 standard deviations. Most of the time you're only going to see them to 2 or 3 because the density gets so small at around 3, and especially at 4, that even though it's not technically 0, it's getting closer and closer to 0 all the time. It's like almost functionally 0, even though it may not actually be 0. And I should mention this is funny too. Again, people like to send me stats-related cartoons and things. This is the normal curvosaurus there. Anyway, the reason I mention this here is, well, what can we do with this normal distribution? What makes it interesting? Well, because we know how the data changes. We know that this is one standard deviation, and we can then start to understand, well, how much of this distribution what's the area under the curve between, say, the mean and one standard deviation, or between the mean and two standard deviations. We can start to understand what the densities look like and convert them to probabilities, and actually be able to know how likely or how probable something is to be in a range between, say, 100 and 140 on this distribution. So one of the ways that we do that is to try to standardize the process, try to standardize how we use this normal distribution. So this is just a normal distribution, again, we're plotting with a mean of 100, standard deviation of 20. What if I were to subtract the mean from all the scores? All right, so if I subtract the mean from all the scores, this is a process known as, it actually has a name, this is a process known as centering. So if I were to center the data, I'll call it centering, by subtracting the mean from all the scores, what that does is it now puts the mean right at 0. It centers the mean at 0. And now we can see that the data to the left and right are moving in terms of the standard deviation. So it goes to 20, 40, 60, 80. And then on the left, it's going negative. Negative 20, negative 40, and negative 80. So it makes the values, the numbers that we're using for the distribution match the symmetry of the actual normal distribution itself. So now the numbers become symmetric the same way that the distribution is symmetric. That's sort of nice, right? So we got numbers that are symmetric and it matches the distribution. But still, there's still something a little more that we want to do with this. So this process centers the data, but we also could do something different. Instead of centering it, we could try to standardize it. So standardizing is the process so forget about centering for a second. So let's go back to the original data. If instead of subtracting the mean from all the scores, what if I just divided all the scores by the standard deviation? So what that does, and it seems kind of weird, the 100 becomes a 5, which is, what does that even mean? Because if I divide 100 by 20, I get 5. If I divide 120 by 20, I get 6. The nice thing about this is, even though it's not centered anymore, it does redefine what a standard deviation is. So it now goes in single units. So what used to be 20, we're now calling 1. Because I divided everything by the standard deviation, it converted the standard deviation to 1 instead of being 20. You're thinking, well, what does that matter? It's sort of just rebranding. It's not really, we haven't done really much of anything, but it's instead of saying that this is, if I have a ruler, right? So instead of saying that, I have a ruler that is going from, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? So I have this ruler, and I'm saying, look, there are 12 inches in this ruler. And somebody else comes along and says, well, that's great, but this is really just 1 foot. Right? So 1 foot is just a rebranding of what 12 inches is. So, and I've turned it into, talking about a single unit. So 1 foot is the same thing as 12 inches. It's the same length, same size, nothing's changed. We didn't squeeze it up, we didn't do anything to it. We just are calling it by a new thing. So what standardizing does for our distribution is the same thing that calling 12 inches a foot. I'm now calling 20 units of this variable 1 standard deviation. I just changed it to moving in single units. This is 1 standard deviation. This is 1 standard deviation. Instead of thinking about it as 20 units, I'm now thinking about it as 1 standard deviation. What if I combine these? If I combine these two processes together, I'm going to center them and I'm going to standardize them by calling each standard deviation 1 unit, 1 standard deviation unit. If I combine them both together, I get the positives of both of those. I get a distribution that's centered at 0, and it also moves in 1 unit. So it's nice and symmetric. I've now rebranded everything so that this is now 1 unit going up. So if it's a positive number, I know it's on the right-hand side. If it's a negative number, I know it's on the left-hand side. It's moving in single units. It's centered at 0. And to do this is now what's creating a standard. If I do both of those things, It's creating a standard normal distribution. So I've gone from a normal distribution to a standard normal distribution. So the only difference is a standard normal has been converted to a standard normal by centering the data, by subtracting the mean from everything, and then also standardizing the data by dividing by the standard deviation. And what that does is it creates a standard distribution with which we can compare all distributions to. Every distribution, every normal distribution can be converted to a standard normal. We can make decisions, estimate, calculate things about that distribution because we know the properties around the standard normal. So we're going to use the standard normal to figure out things like how to convert the densities and stuff into probabilities, and we're going to use all that stuff. So that process of centering, standardizing, creating a standard normal distribution, you might be familiar with it, is sort of, if we convert the raw scores into z-scores. So if I create z-scores out of my raw scores, that is the process of making a standard normal distribution. So z-scores are just the standard normal scores that relates to our raw scores, where these are the raw values, the raw scores, this top line here, right? This 100, 120, 140, those are the raw scores. If I subtract the mean, I'm centering. If I divide by standard deviation, I'm standardizing. If I do both of those things together, right? For each value that I do that for, I'm turning that value into a z-score. If I do it for all of them, I've now converted everything into a standard normal distribution. So all these things are all sort of connected. They're all the same part of the process. So a standard normal distribution is a special version of the normal distribution where the mean is 0, standard deviation is 1. And it's always going to have a mean of 0 and standard deviation of 1 because we centered the data by subtracting the mean from every score, which puts the mean at 0. And then we divided all the scores by the standard deviation to make the standard deviation 1. So the process of taking a normal raw score distribution and converting it into a standard normal distribution is the process of going from raw scores to z-scores. So when you hear standard normal and you hear z-scores, I want you to realize that those two things are the same thing. They're not two different processes or two different things. It's just the z-scores are the individual standard scores within a standard normal distribution. And you see down here, whatever the mean happens to be, this mean happens to be 1,010 with standard deviations of 20, right? If I subtract the mean from everything, divide by the standard deviation, it's going to convert this to a standard normal that has a mean of 0 and standard deviations of 1, 2, 3, positive on the right hand side, and then -1, -2, -3 on the left side. Notice that the size of it, right, the width, the size, the shape, and everything stays the same. It doesn't, by dividing, I'm not making it skinnier, I'm not doing anything to it, it's staying the exact same size, because all we're doing is just renaming these 20 units here between 1010 and 1030 as one standard deviation, but it's the same width, nothing's changed. So let's say you and a friend are both taking 320 this semester or this session or whatever it is, and with different teachers, different classrooms, different teachers. And you earn a 60 on your first midterm and your friend earns a 70. Who did better and why? So if you've ever had discussions with friends about grades, some of this stuff may come up. Oh, I got a 70 on mine. Well, that's really good. I only got a 60 on mine. The problem is this doesn't have enough context for you to know whether 60 is better than 70 or 70 better than 60 because it doesn't tell you anything about the actual distribution. Let me see for a second. Do I have the answer here? No. So let's say you earned a 60 on a test where, so let's say in your class, the mean of the test, say the mean of the mean of the test was 50 with a standard deviation of 5, right? Standard deviation of t is 5. Your friend well, they had, let's say the mean of their test was 70 with a standard deviation of 10 or something. So right away you can start to see that you get the feeling that, all right, wait, just because your friend has a higher score doesn't mean they did better on the test. Because for your test, you got a 60. So your 60 is 60 minus 50 divided by 5, which is 10 over 5, means you got a 2, positive 2. Your friend, because they scored right at the mean, 70 minus 70 over 10, they have a standard score of 0. Now, that could seem scary. We're used to 0, meaning that you got no points or whatever. But in a standard normal distribution, 0 doesn't mean that. Just 0 actually means that you scored at the mean. So if you scored at the mean, that means you're sort of scoring average. Where on your test, your 2 would likely mean you got an A, because you're 2 standard deviations above the mean, which puts you at a very low probability points. So in terms of comparing your test to other students in the class, you scored much higher than the average students, where your friend scored exactly at the average. So even though your score was lower numerically, relative to the class, you're doing much better. Your friend is scoring just about average for the class. So knowing the mean and standard deviation for a distribution tells you a lot about where you sit, where you place in that distribution, and how far away from average you are. So when the question about who did better and why, you can't just look at the score. You also have to look at the other information about the test itself to see where you sort of fit in. Okay, so as we convert raw scores to standard scores, it's a process of creating z-scores. So a z-score indicates how many standard deviations a score is away from the mean. So like in our example there, if you're 2 standard deviations above the mean, that tells you a lot about where you are, where you fall in the distribution of scores. Your score itself, 60, doesn't tell me a whole lot unless it's relative to the mean and standard deviation of the distribution itself. So every z-score has 2 components. The size, which is obviously the 1, 2, 3, 4, whatever the number is, but also the sign. So the sign and magnitude are 2 parts. So again, it's not as concrete as thinking about the number of points. 0 points means you answered no questions, where here 0 means you're at the mean. So it's more about relative place in the distribution of scores as opposed to absolute value of the points. So here, if the sign for a z-score is positive, it means it's above the mean. If it's negative, it means below the mean. And then the magnitude just tells you how far away from the mean it is. But one thing to keep in mind is that if you're a positive 1 and a negative 1 are equally distant away from the mean. So they're the same distance from the mean, regardless of the fact that one's negative and one's positive, because we're assuming the symmetry of the distribution. So to convert a raw score to a z-score, you go through this process where you get if you want whatever z-score you want for a particular score for an individual, you take that individual score, we're going to center it, we're going to subtract the mean, and we're going to divide by the standard deviation. So that ends up being score minus mean over standard deviation is the sort of process. That's how we convert a raw score, like your score of 60 on your test, to a z-score of 2 by simply subtracting the mean, the process of centering we mentioned, and then standardizing it by dividing by the standard deviation, so that way you know how many standard deviations above the mean you are. If I want to go backwards, if I have a z-score, like your z-score of 2, if I want to go backwards and figure out, okay, well, if I have a z-score of 2, what raw score does that correspond to? I want to go the other direction. So by simple algebraic manipulation, we can actually rearrange this into this, where if I have a standard deviation of 2, keep kicking this thing, I have a standard deviation of 2, All right, so I want my raw score. I want xi. I have my z-score of 2. I can multiply that by the standard deviation, which I think said was 5. And I can add back the mean of the test for your class, which I think was 50. And it will tell me what my raw score was. 2 times 5 is 10, plus 50 is 60. This is a way of taking a z-score and converting it back to the raw score. Or another way of thinking about that is standardized scores are great in terms of telling you, how many standard deviation things there are, but it doesn't tell you anything about what the scale is that it was originally measured in. So since these were points on a test, a z-score of 2 doesn't tell you how many points did you earn, how many points did you get on that test. So we can actually use the information, the standard deviation, this is the S, this is the Z, plus the mean for X will give me back to my XI. Actually convert it back to the raw units. So property of z-scores, just to sort of reiterate this, the number, z-score tells you the number of standard deviations you are above or below the mean. Positive z-scores are above, negative z-scores are below. And then we can start to think about the area under the curve for values that are like between two z-scores. We can't really do it for any particular z-score because it's a continuously scored scale. The actual density or probability for any particular number, like 1.47592, is going to be really, really tiny, super, super small, because it's a probability of a very specific, small, continuous value. But what we can do is start to look at, just like we did with the dice probability function, we can actually start to look at, well, what if I wanted the value of below a certain score, or between this score and this score? What's the probability of scoring in between those numbers? Well, I can add up all those values, and I can figure out what then the probability is for ranges of z-scores. And we can do that by calculating the probabilities for the z-scores on the standard scale. Once we convert our raw scores over, we can then use the z-scores to figure out the probabilities. So some more properties. Most z-scores, 99.7 or something % of them, fall between -3 and +3. So this means in a distribution, even though, yes, the normal distribution is asymptotic, and as you go further into the tails, it never really goes to 0. It just gets less and less probable. So as you approach the tails, get above 3s on either side, you're getting less than 1%. It's getting the probability is getting very, very small beyond 3s. So yes, you can figure out the probabilities for 4 or 5 standard deviations, but they're going to be infinitesimally small, very, 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 very small. Okay, so functionally, the majority of the distribution falls between -3 and 3. Right? If you were to round this up, it'd be roughly 100%. So we can get nearly 100% of the scores, or a probability of 1, by looking at just the range between -3 and +3. Z-scores are standardized scores, so this allows for easy comparison of distributions. Like I talked about with your friend and your test, you can actually then compare where you are and look at the distributions separately. It's just a joke. I'm 99.7% confident that I fall between 3 standard deviations from the mean. So this is designed to just to give you an idea of understanding the proportions and things in a Z distribution. So if we look at this, what it tells you is the percentages. This is rounded. That's why it's called rough estimate. So we can look at this this rough estimate chart based on the a z-score, and it gives you an idea of sort of what to expect, where the majority of points or values fall in the distribution, and sort of what to expect when looking at ranges of scores. So for instance, the percentage of scores between, or the probability for scores between 0 and 1 is roughly 0.34. So roughly 34% of scores will fall between the mean and a standard deviation of 1 on either side. So the percentage of scores from 0 to -1 is about the same as it is from 0 to 1, and it's roughly 34% on both sides. As you go beyond that, between 1 and 2 standard deviations is roughly 14%. on both sides. So between -1 and -2 is also 14%. And then as you get above that as well, between 2 and 3%, sorry, a standard deviation of, or z-score of 2 and 3, you're getting roughly an additional 2%. If you add this up, 34 plus 14 is going to be 48, plus 2 is 50. This adds up to 50% on this side and 50% on this side, which covers 100%. This is not, you know, actually true, but again, functionally it sort of works this way. So again, these are rough estimates that are rounded. So it's assuming that because 99.7% of the scores fall between -3 and +3, if you round that up, it's roughly 100. So this is actually assuming 100% is between -3 and 3, even though you can have values beyond -3 and beyond +3. But this gives you an idea. So if you're looking up, trying to figure out the probability of scoring between 0 and 2 standard deviations, we can add these two together and realize, okay, well, it's like 48%. That's a 48%. Or what's the probability that someone's going to score above a standard deviation of 2, +2? Well, there's only 2% there, right? So if we keep these in mind, this can get us pretty far in terms of trying to estimate the percentages for scores, at least as they fall at whole z-score units, like at -1, at -2, or +1, +2. So let's look at how that might work. So if you look at the rough estimate of this thing, it tells you that 50% of the scores are above a z of 0, and 50% are below. So keep that in mind whenever you're trying to look at the probabilities for ranges of scores. If you're on one side of the distribution trying to find a range and you're getting a value that's over 0.5 or over 50%, something's wrong, right? You shouldn't be having that if everything's on one side. 34% is between a z of 0 and z of 1, right? So whether it's +1 or -1 doesn't make a difference. You get 34% between the mean and 1 standard deviation. If you look at between -1 and +1, that covers roughly 68% of the distribution. So go back to that for a second. 34 and 34 is 68. So if I'm going from -1 to +1, that's a huge chunk of the distribution. It's almost 70% of the scores are going to fall right in this middle piece between -1 and +1 standard deviations. If you go out even further and look at -2 and +2, you can add in both those 14%. You're talking about between -2 and +2, 96% of the scores fall between those values. 96. So the majority, by far, 96% of the scores will fall between -2 and +2. This says 99%, but if you actually add them up, it's really 100. But it's really like 99.7% are between -3 and +3, which again, rounding, it is functionally sort of 100%. Okay? So the normal curve and this whole idea of sort of density and area, in any distribution, the portion under the curve can be interpreted as the percentage or probability of scores in the distribution under those values in the curve. So since 68 or 0.68 of the area falls between plus and minus 1 standard deviation, then we assume that 60% of the scores are going to fall under the normal curve between -1 and +1. So this is nothing. This is not. If this seems like, well, why am I saying this is not a revelation? It's just that because the expected probabilities based on the z distribution are 0.68. That's the probability of scores falling between there. We tend to look at and see that if we actually look at scores, well, 68% of them will actually fall between those values, and those two things correspond. So theoretically, they often, they say 0.68 is what we should expect, and then functionally, we'll find somewhere around the same number of the percent of scores will fall in there, and there's a nice correspondence between the sort of theoretical z-score distribution and actual scores falling in a distribution when we go to apply the normal curve. Okay, so let's use this idea of rough estimation to sort of answer some problems, how we might go about figuring that out. So for example, consider a test X, right, with a mean of 50 and a standard deviation of 10 and the variance of 100, right? So if the standard deviation is 10, the variance is 100. Just square the standard deviation to get the variance, so these two things should correspond. at what raw score do 80% of examinees score below? So the first thing that I would do, if ever I'm seeing these problems come up on a test or on a homework or wherever, is to try to line things up. All right, so if this test has a mean of 50 and a standard deviation of 10, I'm going to come right down here. I'm going to write down that, okay, so 0 z-score corresponds to 50 in my raw score. And because it's moving a standard deviation of 10, that means that right next to one standard deviation is 60. This is going to be 70. And way up here is 80. And going the other direction for -1, it's going to be 40, and then 30, and 20. Okay. So there's my raw scores. So I can convert this over and do a z-score conversion, and I'll do that in a second. But if I just write this down, and I realize, okay, if 2 plus 14 is 16, 16 plus 34, up to here is 50%. So it says, at what raw score do 84% of examinees score below? So at what score would I need to have 84% of students do worse than I did? So that means it's going to be looking at things to the left. So up to this point, if I scored at the mean, that means that 50% of students did worse than I did. All right, so I need to go up a little more. So if I score at 1 standard deviation above the mean, 50 plus 34 is 84. Right, so if I were to score at this point in the distribution, right, it would tell me that everything below that distribution here, all this stuff would all fall underneath that distribution. Sorry about the squeaky noise. So if I scored there, the rest of this distribution would all fall below that. So I know that means that if I get a standard deviation of 1, I would be able to score better than 84% of respondents. And because I drew this out, that tells me that I need to score 60. Right, 60 is going to be my, if I scored a 60 on test X, then I would have scored better than 84% of respondents. Now, the way I could have done that is to just convert and figure out, all right, well, what score would I need to correspond? What score? 80%? So I could have figured out that that at 1, I got 84%. So now I need to convert back over. What raw score? And I need to go, okay, I have a z-score of 1. I got to convert back over. So 1 times standard deviation of 10 plus mean of 50 would tell me that I need a 60 on the exam to score better than 84% of respondents. Okay? So I can do that by simply applying this equation, sort of converting it over, but I just did it by sight, by figuring out, okay, when I wrote down 50, 60, 70, 80, and all this stuff, I can see that 60 corresponds with 1 standard deviation, and right away I figure out that if I need 1 standard deviation above the mean to get to 84%, that just means I need to score a raw score of 60 to get that 84%. All right, let's do another one. So here, consider the same test X with a mean of 50, standard deviation of 10. At what percentage of examinees will score greater than 60? What percentage of examinees will score greater than 60? Okay, this is actually related to the last question, because we know 60 corresponded to 84% below, so that means it's going to be 16%, above. But let's just walk through it in case we hadn't seen the last one. We would again write everything down here. So let's think, all right, this is 50 here, right? 60, 70, 80, 40, 30, and 20. So, all right away I can say, okay, so 60 is the score it's asking about, and wants to know what percentage. Well, 60 corresponds again to a z-score of 1. So now what it's asking for is asking for greater than, is it's looking at this number again, but now we're talking about looking at this side of the distribution instead of the larger side. It's looking at this smaller side. Okay. So I want to know what percentage of respondents are going to score in that range above 60. All right, so 14 plus 2, 16. And if you were to answer that on a exam, say, oh, all right, 16%, that'd be right. Okay, this marker might be dying here. 16%. To figure it out the other way around, again, if you know it's asking you about a score of 60, if you don't write this out and sort of look at it this way, what you end up having to do is say, okay, well, score is 60, I got to convert that to a z-score. 60 minus 50, which is the mean. So I want xi minus mean x. Right. So that's going to be over the standard deviation, which is 10. That. So 60 minus 50 is 10 over 10 is 1. So my z corresponds to 1. And then I can figure out, oh, okay, well, 1. So what percentage of scores are above 1? Oh, I know it's 14 and 2, and I can figure out 16%. Or if I just sort of written this out, I wouldn't need to do all this sort of conversion. I could just figure it out that 60 corresponds to 1 and be done with it. Let's do one more. So consider same test again. Test X, mean of 50, standard deviation of 10. Now it's talking about ranges. So what percentage of examinees score between 40 and 60? So again, having this sort of drawn out, the first thing I would do is, again, place this at 50, 60, 70, 80. This would be 40, 30, and 20. Okay, so once I had those, I would then figure out, it's asking about 40 and 60. So it wants to know the range of scores between 40, which corresponds to a -1, and 60, which corresponds to a +1. So it's really asking for everything that's in the middle. It wants to know what percentage of scores are in this part of the distribution between 40 and 60. Okay? So because it falls exactly at -1 and +1, we know that that's 34% plus 34%, which tells me that this piece here is 68%, and I'm done. Right? I don't know, I've basically figured out what the answer is by just knowing where these correspond and knowing that 1 and -1 correspond to 34% away from the mean. I can just add them together. The other way, I'd have to convert both of them. If I want, going through the more technical route, I have to do, all right, 40 minus 50 over 10 equals -1. 60 minus 50 over 10 equals 1. Figure out that, all right, the mean of 1, so I can convert these out. Where if I had just written this out this way, it saves me a lot of that sort of having to do the equations and things. That only really works, though, when the values fall exactly at a standard deviation. Knowing that it's 50 in the mean, and the standard deviation is 10, that means I know that 60 is at 1 standard deviation, 40 is at -1. It helps to sort of plot these things out a little bit. Drawing a picture and sort of figuring out will help you avoid making mistakes when answering questions about area and the curve and that sort of thing.